Okay, so for 9.6 activity series, the main things you need to know are that an activity series is a list of substances ranked in order of their relative reactivity to one another. So, for example, magnesium can knock hydrogen ions out of solution, so it's therefore considered more reactive than elemental hydrogen, etc., etc. In this table here, it shows you a list of reactivities of the different metals. So this is a metal activity series with the most reactive on the top and the least reactive on the bottom. Notice also that this specifically says that these will displace hydrogen from water, steam, or acids, so liquid water, gaseous water, or acids. So over here it has H2O written as a liquid, and then when we get to the next section it's only H2O as gases. Okay, so it won't displace water. So these things react very violently. They produce these bases in hydrogen gas and get hot and can be very explosive. So these are not found in nature. They're stored in oil in a container, and they're extremely hard to get because you have to have a special license to have them. The next ones here only react with steam or acids, and I mean we've all used this year already magnesium, aluminum. You used manganese dioxide, zinc, iron. These are all things that we have in the lab. You've been using them. And then here, these are things that just react with acids. So this H+, this means it could be like HCl, H2SO4, nitric acid, any of those. Okay, so this just means with any acid. And these ones that are down here below this line, it means that they do not react with water or acid or anything. They just kind of hang out. So they're more unreactive. You would think that we could just look at the periodic table. So in Unit 5, we said that reactivity increases as you go down. So sodium's more reactive than lithium, and potassium than sodium, etc. But if you look at this list, that's not actually what we find. We find that lithium is actually more reactive than potassium. So while the overall general ideas of reactivity going down are true, for metals, there are other properties of metals that are making it so there's a lot of exceptions, which is why we use this activity series to determine if something will happen. So let me give you a couple examples that you can solve in your groups to say what is actually happening. So for example, if I react Fe, let's say NO3, so iron nitrate, with aluminum. At your group, if you could please tell me whether or not something's going to happen. So use the activity series to determine whether there's no reaction or there's actually going to be a reaction. Okay, so if we take a look at Fe and Al, so we're saying which one of these is more reactive, we can come up here and look at our chart and say, well, where are they on here? Aluminum is higher in the reactivity series than iron. So aluminum wants to steal iron's date, is basically what we're saying. Aluminum is going to come in and displace iron and take nitrate home, and then iron's all by itself. So you're literally saying, will this one replace that one or not? So we would have a reaction. Aluminum is now with nitrate, and iron goes home all alone. Okay. Let's do another example. Let's say we have copper sulfate with silver. Okay, in your groups, go ahead and determine whether or not there will be a reaction and why. Okay, so we're trying to determine if silver can come in and outdo copper. So if we look at our chart here, copper is more reactive than silver. So copper wants to keep its date more than silver can steal its date. So no, nothing will happen. You would simply just write no reaction. Okay? So what we're going to do today in the lab on the next page, so if you turn your paper over here, you are going to be reacting 5 metals with other metals or with an acid to determine whether or not one's more reactive than the other. While you're doing this, I do not want you to use this chart. Okay, this is all going to be based on what actually happens in the lab. So don't look at the chart and say, well, something should have happened. I want you to do this based on, does something actually happen? we're going to rank these in order of reactive to non-reactive based on your data that you're about to collect. And then there's a series of questions that we'll answer at the end. So there's no instructions on here, but what you're going to do, notice up here it has reactions 1 through 6. Your evidence of reaction, just like we did in the last lab. So is there a color change? Is there bubbles? Is there heat? Does it smell? That's what you're writing here. Then if something does happen, right, you're going to balance the equation out. If nothing happens, you're going to write NR, no reaction. Then you're going to rank them down here for each reaction and answer the questions on the back. We're actually substituting in all of our leads for iron. So let's go ahead and fix that right now. Instead of lead here, you're going to be writing iron. And instead of lead here, you're going to be using iron. And then there's a question on the back that also says lead, so we need to change that to iron.
Why are we doing iron instead of lead? Because lead's bad for you?
Nope. The lead reactions weren't working as well as I wanted them to. Okay, the other thing is you're not doing these reactions in a test tube, you're doing them in a well plate. And a well plate is a little dish that you put a little bit of each in. Leah, can you grab me a well plate from the back? Okay, so here we have a well plate. It's called a well because it has a series of little dips in it, so it looks like it has a bunch of wells. There are 9 places where you could do a reaction here, but you're only doing 6. So when you do each reaction, you need to probably put this on like a paper towel or a piece of paper and label where you've put what, so you know what's happening. The reactions don't happen instantly, so I would like do one and then do the next, like get them all done, and then wait about 10 minutes and see if something's happening. You can also use a stir rod and kind of like stir them in there. Don't go from one to the next, though, without cleaning your stir rod, because then you're going to get things mixed up and something might appear to happen that didn't happen, okay? So everything you need is in the back. You're going to use just a little bit of metal with a little bit of solution. You don't need a lot of them, right? That's why we're doing a little bit of the reactions instead of like on a big scale, okay?